Now again, because cheapest link is not an algorithm that's presented in your textbook, I have a couple additional examples so you can practice running through this algorithm. I would encourage you to try these 3 examples on your own before you kind of see the solution process for these. Alright, so assuming that you've tried these on your own, let's go through how to answer these. So it says, using the cheapest link algorithm, find the approximate solution to the TSP. In your work, write the weights in the order found, and then write your tour starting and ending at vertex A. In this first graph, the lowest weight is going to be 9. The next lowest weight is the 12. After that, I skip the 15 because that's 3 edges coming out of D. I skip this 30 because it would create a circuit right here. So we grab this 30, and then finally the 43 to close the circuit. This gives me an overall weight of 94, and then writing the circuit from vertex A, it would be A, B, D, C, and A, or I would also accept the mirror image. Now I want you to take a look. Actually, we solved this one earlier in our handout. So scrolling up here, there it is. Alright, we solved that one actually using brute force. Using brute force, we got that the optimal solution was going to be this circuit with a weight of 87, and we actually got the nearest neighbor algorithm was being 97. So out of the 3 possible kind of unique circuits, because again these ones are the mirror images so they'll have the same weight, notice that the cheapest link algorithm did not get me the optimal solution, and it also yielded me a solution different than what nearest neighbor is finding. So nearest neighbor found the worst option, the optimal solution is this, cheapest link got me a little bit closer because it got me that weight of 94. Okay, so let's come back to this next example then. Scrolling all the way down here. Alright, there we are. Alright, so for this next one, running through the cheapest link algorithm, the lowest weight is 1. The next lowest weight is the 7. At that point in time, I don't get to grab the 8 because that would create a little circuit right here. I don't get to grab the 9 because that's 3 edges coming out of vertex C. The next one I would grab is the 10. Then the 14. Now at this point in time I only have this one more edge to close my circuit. This has an overall weight of 182. And then writing this circuit from vertex A would be A, E, C, D, B, A, or I would also accept the mirror image. Now for this particular graph, we actually did also see this one earlier. We ran through nearest neighbor on this. So notice on cheapest link we got an overall weight of 182. Let's scroll back up here. Okay, so the 182, we could actually verify that the 182 is going to be this circuit, but just with a different starting vertex. When we ran repetitive nearest neighbor on that, that was actually the worst option out of all of them that we found. And that's going to be the option that cheapest link actually gave us. On this one, when we ran repetitive nearest neighbor, we got that the lowest weight was 120. And then also keep in mind, if we just ran nearest neighbor out of vertex A, we would have gotten 178. So nearest neighbor, repetitive nearest neighbor, and cheapest link all would give us different weights because they're all focusing on different aspects of the graph. As a fun fact moving forward on this, if you were to solve this graph using brute force, you would find that the optimal solution, which means then you, out of these 24 Hamilton circuits, you would be finding those 12 unique ones. Out of those 12 unique ones, you would be finding the weights of every single one of them. You would find that the optimal solution will have a weight of 116. And the tour would be A, B, E, D, C, A, or the mirror image of this would also work. So notice that the nearest neighbor, repetitive nearest neighbor, or cheapest link, none of them gave me the optimal solution for this graph. All right, so scrolling back down here, we had one more that I wanted you to work through. Now for this graph down here, the lowest weight is 2. So I would mark it. And then the next lowest weight is 3, and I would mark it. Now at this point in time, the next lowest weight is 5, and there are 2 different 5s in this graph. Depending on which one you grab, it actually would produce a slightly different solution. So I'm going to go ahead and make a copy of this. And put it over here. Little baby version of this graph. So then we'll talk through the 2 different solutions that are available on this one. Now either one of them would be possible depending on which 5 you grabbed. So let's say for instance you grabbed this 5. So then you would mark it. Now at this point in time, the other 5 is no longer an option because it would create 3 edges out of vertex F. So you would omit that one. Let's see here. Then the next lowest one would be 7. This one creates 3 edges coming out of F. That's no good. This 7 creates a circuit right here, so that's no good. The next viable option you would grab is this 8. That's up here. Running through here, 9's no good. That creates 3 edges out of vertex E. Out of the other numbers available, 23 would be my next one. And that one's okay to grab. Now we've had a critical point in the solution process. So I just have to grab one more edge to close this because I have 1, 2, 3, 4, 5, 6 vertices. And so far I only have 5 edges. So to close this, it would be the 75. So this is the order that I'm going to grab the edges, which gives me an overall weight of 116. And then stating the 2 are out of vertex A, you would have A, B, D, C, E, F, and then back to A, or the mirror image. Now let's say then out of this 2 and the 3, you didn't grab this one next. Let's say you grabbed this one. Okay, so if you grab that one, then the other 5 is out because it would create 3 edges out of vertex F. That would be no good. This 7 is no good because it would create 3 edges out of vertex F, but this 7 would be okay. So we would grab it. This 8 would be okay. It doesn't create a circuit, and it doesn't create 3 edges out of any vertex. Oh, so hold on here, I messed up. I needed to write that 5. We're going to move all these up. So I would have the 5, then this 7, then that 8, and then finally I have 1, 2, 3, 4, 5 vertices. So now I just need to close this. So what edge is going to close this for me? It would be this connection right here. So I would grab that. Adding all these up, it gives me a weight of 70. And then this guy's tour is A, then D, then B, then F, then E, C, and then back to A, or the mirror image. So you wouldn't have to do both of these, but on this example I wanted you to see, depending on which 5 you picked, then it precludes being able to grab that other 5, and then it totally then adjusts the results of the graph from there on out. So let's summarize everything that we've seen so far in this TSP kind of problem set. Now, if you can find an algorithm that is both efficient, which means you can get through it rather quickly, and gives you the optimal solution, then you would get $1 million. And no joke, you would get $1 million. This is actually one of the problems that's right now known as the Millennium Problems. So this website talks about these various Millennium Problems. Finding both an algorithm that is optimal and efficient is known as the P versus NP problem. So that would be then when you look at these Hamilton paths and circuits, when you want to have these types of problems where you don't go back to a vertex more than once and you want to make sure that you're guaranteed to have the optimal solution, we don't know a way to do that without doing it using brute force, which our computers can't handle. So if you can easily find a solution, this company, this organization, would give you $1 million for it. And you would actually get more than $1 million with all of the publicity and different things that you would get after the fact. So right now, if you want the optimal solution, well, then you have to do an inefficient algorithm. You have to solve it using brute force. That is the only way to guarantee the optimal solution. Now, if you're willing to just get an approximate solution, so one that you hope was relatively close to the optimal solution, and we've seen in some examples that these approximate algorithms could actually get us the solution that is furthest from the optimal solution that is even possible. But if at that point in time you'd only know how close you are, where if you ran brute force on that problem on those vertices, but otherwise if you're just going to run the approximate or look for an approximate solution, then you would be running these more efficient algorithms, and that's where we talked about nearest neighbor. And then repetitive nearest neighbor. Or cheapest link. Okay, so the fact that these are called approximate algorithms mean that they do not guarantee to get us the optimal solution. They get us what is known as the approximate solution, which we hope is relatively close to the optimal solution, and we can run through them very efficiently. Now down here, if we were to have an inefficient algorithm that also got us the approximate solution, why would you bother with something like that? Okay, it's going to take you a long time to get through, and you're only guaranteed to get the approximate solution. Why are you messing around with that? Okay, so the trade-off here is that we are not guaranteed to get the best solution, but we can get through these algorithms fairly quickly. Okay, so this is then kind of the summary of the algorithms that we've talked about so far. Now, just to kind of sum up everything that we've seen so far, let's return back to this problem that was kind of our motivating problem all the way back at the beginning of the first page of this handout. I had said, hey, just try to see if you can find that optimal solution. Most students, when they think about one way they want to solve this problem, they usually come up with one of the algorithms that we've talked about so far. Now, as an FYI, there are other algorithms that solve these TSPs that we have not talked about. Okay, so we only covered 3 algorithms, now technically 4, 3 approximate and 1 optimal but inefficient algorithm, but there is even other ones than that, and obviously all of the other ones fall up into this category up here, where you can get through them rather quickly, but you're only guaranteed to get the approximate solution. Now for this one, what if we were to solve this using cheapest link? Now cheapest link says then, okay, so the smallest weight I'm seeing anywhere in the graph is this 119. I would grab it. The next smallest number anywhere would be the 120. I would grab it. The 121 would be out because that's 3 edges coming out of vertex C. The 133 would be out because that would create a circuit up here. This 150 would be okay. This 152 would be okay. Now at this point in time, I just need to close up my circuit because I have 5 vertices here and I already have 4 edges. So then the edge to close up this circuit would be this 200. Overall then, I get a weight for the cheapest link algorithm of 741. Now if we were to look back, we solved this problem, or we looked at it rather, when we solved the repetitive nearest neighbor, and 741 was one of the weights that we got when we ran the nearest neighbor out of vertex E. So we would get this same tour that we got right here from cheapest link, but when we ran repetitive nearest neighbor, we actually found that wasn't the best weight. The best weight that we got out of that one was the 722. If you were to solve this problem using brute force, because this one has 5 vertices, this means there's 5 minus 1 factorial, or 4 factorial, or 24 possible Hamilton circuits. Now you only have to find the weights for the 12 unique ones, because then the other 12 are just going to be mirror images. Right here I have a table for those 12 unique Hamilton circuits, because here are their mirror images over here. That gives you your 24 Hamilton circuits total. Right here we have designated this is what's going to be the optimal solution to this problem. So the optimal solution will ultimately have a weight of 676. So if you were able to get that weight, if you just kind of looked at this graph and tried a couple of them and you happened to stumble across this path that has a weight of 676, that's awesome, because you actually did find the optimal solution for that problem.